Okay, so now that we have looked at Gauss's law, and again, just going back to our content on Blackboard for my students, you had the notes on why we had Gauss's law, how we actually got Gauss's law from the different electric field methods, and then looking at it for the spherical, cylindrical, and flat sheets. And that set up what we were doing there. But what we're going to end up having is some applications. Now, back when we did P255, we had several different examples. So while I gave us in this class our whole spherical symmetry for Gauss's law, and we went through all the arguments for that one, then we had from the general physics actually applying it to a situation where I had some spherical symmetry. And this one we had concentric spherical shells that were being used. And it specified the amount of charge on each one. And because of that, we could figure out at different points in the system how much charge was inside the Gaussian surface, what was the surface area, and then pull that together to actually get the value for the electric field. And we had similar things here for a cylinder. In this case, it was just a long, straight wire carrying charge. And we had the plane symmetry. And we talked about that in terms of a non-conducting sheet. But then we also had talking about what was going on with a conducting sheet. We haven't gotten to the conducting sheet in this class yet, but we've done the non-conducting. So rather than go over all of those examples again, I'm going to list these ones here. And mention that the textbooks often have these ones as well. One of them that they often have is a spherical volume and finding the amount of electric field inside that spherical volume if you have a uniform charge distribution. So if you go back and you look at those are going to give you some more examples. What we want to do here, though, for our P401 is we want to move into some more complicated ones. We'll talk about this in a little bit more detail, but in specific, because of the math that we have available to us, we can deal with non-uniform charge densities. Although we do have to be careful because depending on how it's non-uniform, it may break the symmetry. So we have to have non-uniform charge densities that maintain the charge symmetry that we need. Okay? So the first example that I'm going to have you guys look at here, or that we're going to look at together, is going to be for a spherical shell, but it's going to be a thick shell with non-uniform density. And I'm doing this one just because, again, the simpler cases have already been done. And so we can go back and look at those as comparison. And I'll mention some of these things. So now what I want to do is I want to remind us of what our situation here is. And so we've got our integral of E dot dA I'm trying to remember the LaTeX source for that. Okay, and that's got to be equal to the fraction of Q enclosed over R epsilon naught. Hopefully I got that all. And not in quotation marks. So this is our basic equation. I should have had this formatted before I started the video there. So the left-hand side of this is what we've already looked at in terms of being able to reduce this down to something which is easier to work with. And it's going to be the electric field times the surface area of our Gaussian. But in order to find the right-hand side here, I'm going to start writing this out by hand because it's just a lot easier. We've got the 1 over epsilon naught. We're going to have to integrate dq d tau over that spherical shell. Now, because we've got spherical symmetry, we want to use the d tau that's given to us for spherical symmetry. So coming over here, we're going to grab real quick. Actually, I'm just going to open it up from our videos. No, from our previous stuff. The covers of the textbook. And grab our spherical in here. And I just realized that I wrote this wrong. It's the integral of dq, which becomes the integral of rho d tau. It's not dq d tau. And so I'm going to have to specify some of this. Now, I haven't said what my rho is yet, just that it's not a constant. But I can break this down into my 3 integrals. And my d tau is going to become r squared sine theta dr d theta d phi. Because it's a thick shell, it's going to go from some r1 to some r2. But phi is going to go from 0 to pi, theta is going to go from 0 to pi, and phi is going to go from 0 to 2 pi over the entire sphere. So as long as our rho maintains radial symmetry, otherwise the electric field will not be uniform on that spherical symmetry. So rho cannot depend on theta or phi. So the first thing I'm going to do is I'm going to go ahead and separate this, because these are separable as long as rho is only a function. So I've got 0 to 2 pi of d phi. I've got 0 to pi of sine theta d theta. And then the integral from r1 to r2 of my rho r squared dr. Now I'm going to go ahead and pick a nice rho so that I can do this easier. But I can simplify this down already, because since I have a spherical symmetry and it's going over the full sphere, over here I'm going to have just 2 pi, and here I'm going to have a factor of 2. And then I'm going to have my integral. And if you're not quite sure how I got those ones, go back and look at our other examples of integrating over a sphere to see how those ones came out. So I'm going to take now just the look at the radial part. So I'm integrating from some r1 to some r2, some rho r squared dr. Now, at this point, I could do a uniform density, in which case it would pull out, and we would have the integral with a rho on the outside of r squared dr, and that would give us rho 1/3 r cubed evaluated over the two boundaries. But I could also do a non-uniform charge density. Let's use a charge density which is equal to C times R. Now, just to put this into some other terms, at the very center, R is equal to 0, and so R is equal to 0. And as you move out, you get a higher charge density. Now, since I only have a shell, I've got some R1 and R2, so I'm going to have values for the density. There is no 0 density on this particular one. Okay? So the integral of CR R squared dr from R1 to R2. Well, in this case, I've got basically the integral of a CR cubed dr. And so that's going to give me C over 4 r to the 4th evaluated over 2, R1 and R2. So I could take this along with what I found from my other stuff, and I'm going to have, for the full right side, I've got 4 pi over epsilon naught C over 4 r squared to the 4th minus r1 to the 4th. And this is ought to all be equal to E times the 4 pi capital R squared. But I need to stop and be more careful, because the charge inside, that density was only in the R1 to R4 region, which is why we only integrated that from the R1 to the R1 to the R2 region. In order for that to be the charge enclosed, what I really had to have here was a thick spherical shell, and these are not perfectly spheres, which I apologize for because I'm not drawing that well, and then a Gaussian R that's out here. So what I'm saying here is, if my R is larger than R2, then I enclose that entire thick shell, and that's the amount of charge. But I've got 2 other regions of interest. One of them is pretty easy to picture. If my R is less than R1, I've got no charge enclosed. If my R is between those 2 radiuses, only part of the shell was enclosed, And I would really integrate from R1 to R, capital R. So I'm going to take one more page here and just sort of expand this out here then for the three cases. My electric field times my 4 pi r squared would have to be equal to what I've got here, 4 pi epsilon naught c over 4, etc. I'm just going to copy and paste this. Sorry, fixing this. There we go. And then for R1 less than R but less than R2, I would have an E times 4 pi r squared equals 4 pi epsilon naught c over 4 r to the 4th minus r1 to the 4th. And lastly, for r less than r1, I would have E 4 pi r squared equals 4 pi epsilon naught 0. Now obviously these can each be simplified a little bit more. This one is going to give us just E equals 0. Here, if I look at all my factors, I've got different 4 pi's in different places, and things are going to somewhat cancel out, and I could rewrite this one as E is equal to C over epsilon naught 4, because the 4 pi and the 4 pi canceled, and then I would have r squared minus r1 to the 4th over r squared. And up here I would have E is equal to, again, the C over epsilon naught 4, and I would have, r2 to the 4th over capital R squared minus r1 to the 4th over capital R squared. So it depends a little bit on those proportions. Now initially this might look like, wait a minute, are our dimensions okay on all of this? And so I want to remind you in terms of our dimensions, rho has to be equal to some charge over some volume. And we said that rho was equal to C times R. So that means this C has to be equal to Q over V times R. So it's got to be some charge over some length to the fourth. Wait, I think I've got something. I may have to look at this more carefully. Nope, it works. Because typically what I'm going to have for this sort of situation is I'd have some sort of Q over epsilon naught and some area type unit. And so what I've got is up on top, I've got a C, and so that's going to be a Q per length to the fourth. I've got the epsilon naught on the bottom. The 4 doesn't really matter much. And then in my parentheses, it's something like a length squared. So this is the same thing as a Q per epsilon naught length squared. So that's the type of dimensions we would expect to get. So the dimensions are kind of hidden in that constant within the charge density. Okay? Okay, so that is an example of a more complicated Gaussian symmetry where instead of just working with a spherical volume and just saying this is how much charge is involved, we had to go through and figure out how much charge was involved using the integral of the density over the volume.